Okay, thank you. Hi, everybody. And first, apologies that I couldn't make it there in person, but hopefully this will still be worth your time. Okay, so maybe just as a quick introduction to give you some context. So I'm with the Center for Secure Water at the University of Illinois Urbana-Champaign, more specifically with the Civil Environmental Engineering Department. But my background has been a bit all over the place. Before I spent actually about half of my career as a science researcher at mostly national labs at NASA and NOAA, and then transitioned into more programmatic roles and working with data, big data, and innovation. And before coming to the University of Illinois in early 2024. I was actually for over 5 years at Amazon and Amazon Web Services in their sustainability teams. And that's partly why I got so interested in this subject we're going to talk about today. So before we jump into it, I have a few terms and definitions that I wanted to share just to make sure that we're all on the same page when we are talking about different things throughout the conversation. And one of them is the term climate. And I know this term is not an easy one these days because in some situations it's been a bit politicized, but I wanted to take us back to the actual scientific terms. So when I talk about it, you understand what I mean. So when we talk about climate, we talk about the average weather. So you all have the experience when you go visit some place, you try to understand what is the expected temperature I should get around this time of year. And I just posted there for Champaign, Illinois. If you Google that, you'll get that the weather averages or climate for the months of June are, in general, you should expect to have temperatures in the 80s, the higher ones and the lower ones in the 60s and the lower 60s, and you get an average of about 7 days of rainfall per month. So that's the climate. That's what you expect to get. But then the weather is what you really get, right? If I go and visit Champaign, Illinois, I know that today might be, in the 90s or in the 70s. It doesn't really match what the climate is telling me because it's an average, but it's the weather is what I'm getting. So just keep that in mind when I say the climate is changing. It means that those expectations that we have of the temperature, the precipitation, and all of those variables are not consistent with what we've seen in the past. They are shifting, right? And then more specifically, when I talk about hydroclimate, so hydro water climate, so the climate of water is, again, more specifically, I said before, there's 7 days of rain, but can we break that down by season, for instance, and understand that generally in Illinois, we have wetter springs. And we tend to have some rain in the summer, and some of those things are changing. And there's major implications when we start to have changes in the way we are receiving, for instance, water into our systems. Okay. All right. And then the last one I wanted to mention, I think this is the last one, is when I talk about climate projections, I'm really talking about simulations. And okay, let's step back a little bit. When you hear the weather forecast, right? Basically, there's a lot there's much more certainty in that expectation. So they took all these physical principles about different variables relate to each other. They write that into mathematical models that they call these climate models. And when they run that for short-term periods, we kind of know pretty well what's happening, right? Because we know the conditions. So unless you are in very difficult terrains like mountains and things like that, you can pretty well predict what's going to happen. Of course, there's some chaotic nature in the weather that is not deterministic, so we cannot completely control the outcomes. So sometimes it goes sideways, but for the most part, we can do that with weather. When we talk about climate, we are running those similar models at larger scale in way into the future, right? Imagine like 10, 15, 20, 50, even 100 years out. And in those situations, we don't fully know what conditions we will have in the planet. For instance, we don't know how much population we're going to have, how many people are going to have cars and are emitting emissions into the atmosphere. We don't know if we're going to have an eruption of a volcano that is going to put aerosols. And all of that has implications in what we're going to see. And so what climatologists, so scientists do, is they create scenarios. They said, for this scenario, we will have this kind of climate or, expected weather at that time. So when I talk about the projections for climate, I'm talking about the simulations that are basically saying, with this understanding of the system that we have now for those scenarios, this is what we expect. Okay. And they're pretty robust at this point, our understanding. Okay, but now let us take it to the main topic today, which is water. More specifically, how it relates to AI and the data centers and all of that. So we're going to jump into that. But let me start with some basics about water. I believe most people know about this, but I just think it's an important refresher to understand how important water is and actually how important it is, how scarce it is, which is the problem, right? So when we look at our planet, we have about 70% of the surface of the planet covered with water, but only 3% of that total water is fresh water. And this matters because that's the water that we use for everything we do, pretty much, right? So, of all that water, actually 2.5% is not really accessible. It's trapped in polar caps and in icebergs and things that we don't actually have access to easily. So that really leaves us about 0.5% of all the water in the planet as fresh water that we can use. Okay. And most of that water we access, as you look at the water cycle, you probably all have studied this in school before. I know it's very basic, but I just wanted to show all that water basically is circulating in the system, and some of it is in the groundwater that we tap and extract, and some of it evaporates and goes to the clouds and then rains down as precipitation. And then so the cycle does its thing. And we are tapping primarily in the water for our purposes of the discussion today and the different use for water for the water that is in the land part of the equation. So one of the big issues is that that water, the potable water, the 0.5% that we're talking about, is not really evenly distributed around the world. And that creates a lot of problems. One of the problems is experiencing water stress, which you probably have heard about. And that really happens when the demand for fresh water is higher than the supply. And that's happening more than it should happen for many different reasons, because of that uneven distribution, but because even if you have a lot of water in one given location, you still need to have the infrastructure to distribute that water to the people that need it. And that's not always easy or implementable in most parts of the world. And we're still experiencing some of those issues even in developing countries where infrastructure is deteriorating, is aging, and we have leakages and other things. And so the system is complicated. Okay. But so just to give you an idea, according to the United Nations Water Program, about 10% of the global population of the world, which is more than 700 million people, live in countries where they have high and critical water stress. So that means that for the most part, all the time, they don't have water, access to water, right? It's not just like once in a while. It's like when you have high stress or critical stress, we're really in really serious conditions. And that has led the United Nations and the world in general to actually create, I don't know how many of you have heard about the Sustainable Development Goals, but it's a set of goals that all the countries in the United Nations have decided to set forth. And one of them is water. It's basically, let's try to get everybody in the world to access safe drinking water and sanitation and hygiene. And it's not trivial for many reasons, but one of them is, some of them are the ones I described before. Okay. So, okay, this is when we start talking about AI. And I wanted to bring this up. And again, I mentioned this. I was curious about this topic, being the managing director for a center that works on water and having had my experience with the big, the cloud provider world and the data center. So I don't know how many of you are familiar, but AI, they're basically this big mathematical models that are trying to replicate or improve human intelligence. They need to run on these very heavy, complex machines. And those machines or servers are a lot of them put together in what we call data centers. So data centers can have many different sizes, but basically what it means is that you have a bunch of computers co-located with each other doing this computational work constantly. So they run basically 24/7. And and we store data there, so they are not used just for AI. We've been having data centers for a long time, and for instance, the pictures and the data that is in your phone is likely stored somewhere in a cloud. So a cloud is basically this collection of servers in a data center that you can access remotely. So all these data centers are kind of like growing exponentially around the world for many reasons, because we use a lot of data for many applications these days, but AI has really pushed that forward. And so I wanted to show you just the dimension of what we're talking about. So when I put together this slide, which was last fall, so I have to admit I haven't updated those numbers if there's an update, but the last estimate that I came across was that there were about 11,000 globally data centers. And the US, and that one I checked, the US is more than half of those data centers in our country. So that means that we have more data centers than all the other countries combined. And if you look at, I found that image that has a general, this data is normally not easily accessible. People don't actually, even the big data providers, the big cloud providers don't put out specifically where the data centers are. A lot of it for security reasons. But there's some groups that are trying to monitor that. And so the map there, as you can see, illustrates the big hubs of where you will have a lot of activity and number of data centers. And keep in mind, not all data centers are the huge ones, right? But if you look at the map, you can see that the largest concentration is in Virginia because of the proximity with DC and all the connectivity. And that's actually considered the largest data center place in the world. It's in Virginia. But then, behind it, we have a lot in Texas and in California. And you will see, you can see there that our region, Illinois and Chicago, is one of the big hubs as well. And so I think it's important for us to just talk about these things. What does it mean if all these data centers are coming into our backyard and they're growing so fast? What does this mean, right? What do we need to know and what do we need to pay attention to? And I just want to say up front, I am not one of those people that are like, oh, let's stop it. We shouldn't let data centers grow or AI expand. It's a reality. I believe it's here to stay. I just think that, like anything else, we need to create some guardrails and more transparency so we understand what's going on and how we manage it properly so we allow it to grow in a sustainable way. So I just want to say that before I move forward. Okay, so when we talk about data centers, so these big aggregations of computers that are co-located, there's certain things that you need to keep in mind. So when they come into a location, there's many different criteria that are that they consider when they're putting together a data center and selecting a location. For instance, you need flat land, you need access to energy and water, you need to have a lot of connectivity, good connectivity, and that's why most of them tend to be close to big, urban centers. But at the same time, you need land, so it tends to stay more in the peripheral area. And then you need to have skilled workforce to support it. And anyway, so there's many different factors. But then when you put one of those data centers, it is going to take some resources from those places, right? And from the global world, and I'll talk more about that. But one of them is water, and I'll explain a little bit more why the water comes into the equation. Energy, you're probably more familiar with the energy part of the conversation because that's traditionally what we hear more about. These computers take a lot of energy. There's the carbon footprint because depending on what energy you're using to run these data centers that again are running 24/7, you can run into a lot of carbon emissions. And then land use and urban planning can be an issue because they are not always fully integrated into the planning for the communities and where they are located. And there's several stories of a lot of these data centers taking over some of the agricultural land. So all things that we need to consider as we are trying to help manage this process moving forward. Uh, they tend to have a lot of generators because one of the things that cannot happen is they cannot stop running. They have to go 24/7. So that means that they have to have all these backup systems and they run a lot of generators, which can create some noise and some air pollution, some issues of environmental justice, but just because they tend to go and be located in areas that are less affluent. And then there's the e-waste, the electronic waste, which is another thing. Some of these data centers, or the majority of these data centers, have a turnaround life cycle of about 3 to 5 years. So a question to ask is like, once you decommission all of that equipment, who's responsible to get rid of it? Is it the local community that is hosting the data center? Is it the cloud provider? So all things that we need to consider. Okay, but just digging down a little bit deeper into the data center and the water. Uh, okay, so this, as I said, these data centers consume a lot of power, right? And you probably all, I don't know how many, I cannot see the audience, so I don't know your age, but if you're a little bit older like me, you'll remember the time when your computers, if the battery got hot, they would shut down, right? And even your phone, if you got really hot, you would shut down because heat is really bad for computer systems. It can completely destroy the equipment, or at the best worst case scenario, it will impact the computational ability of the system. So you can have data errors or data missing and things like that. So one of the things that these data centers have to do is absolutely keep these servers cold. Not cold, there's a range of temperature, but they have a very rigid temperature at which they can operate and they cannot deviate from that. So that is like a prime operational byproduct of running these data centers is that you need to find ways to cool it. And the most traditional way to cool these data centers and the most efficient way is using water. What they do is actually have these gigantic tanks of water that circulate through the area where the servers are and they cool it down. There's very different methods to do that. There's ways to do it with electricity where you basically have AC or big pumps and fans running through the systems. But the most efficient way they've found so far that is proven and reliable is to use water systems and the water tanks. And so what that means is that that uses a lot of water. So I wanted to talk about the big picture of the water with data centers, because there's that part of the equation I was just telling you about, which is the cooling and using the cooling towers, which uses a lot of water, right? But then there's another part which we call like scope two. So the way we measure our water is being used is like in this weird terms, scope one, scope two, scope three, that for you that are the ones of you that have been involved or track at all greenhouse gas emissions will be familiar with those terms because it's the same. So scope one is direct consumption of the water or production of carbon, but let's focus on the water. So how do you, like a data center would use directly water, the cooling, right? That's the majority. The scope two is what is the water that is used indirectly? And indirectly can be anything, for instance, all the energy that is being used to feed the data center came from thermal electric energy or some kind of hydropower. It has a water footprint. You need to have that water available to produce the energy that is going to feed the data center, right? And then there's the scope three is anything that has to do with the water that is used in basically the value chain or the supply chain. Sorry, I should be saying supply chain. So what he means there is that, for instance, all the semiconductors and all the chips that are going into those servers had to be created. And that industry actually consumes tons of water. A typical facility for a semiconductor or chip consumes on average 5 million gallons of water per day. So when you add it all together for all the different pieces, and then you add that to the water that was used to produce the electricity and then you add the water for the cooling, you start to have a really big water footprint for these data centers, right? Some of it is not local, right? Because if those chips came from the other side of the world, they're not consuming the water locally, and the energy could be coming from other regionally, other locations, but it's still part of the footprint of that data center. So I wanted to give you a little bit of numbers. We don't have many numbers, and that's part of the problem. So there's no real requirements right now to disclose how much water these data centers are consuming. But there's been some studies, like a few, and one of them has shown that, for instance, training the GPT-3 model, which is, not even the most updated one, in a state-of-the-art Microsoft data center would consume around 700,000 liters. Wait, I cannot read because I have my image on top of it. Or about, which is equivalent to about 185,000 gallons of water. And I did a quick search on what would that mean in terms of if you leave your faucet running continuously 24/7 in your backyard, how much water would that be? And he said it would be just over 17 days. So that's the part of actually training the model, which is the part of the equation that requires the most energy. They run it continuously, this model, for maybe a full week to 10 days or even longer. And that's training the model to know how to detect what it needs to do, right? To create all the algorithm. And then the other part is the inference. So when you go into Chat GPT and you ask a question, the model is already created in the back. You basically just asking it to infer based on the knowledge and the mental model that created what is the answer that makes more sense given your question. And that consumes much less, right? Because you're not running all those calculations. And so the average, they say for GPT-4 is that if you do an interaction of about, for a 100-word response, it consumes about half a liter or about 17 ounces of water per interaction. So just, I wanted to mention that, bear in mind that this is an average, and it's probably, whatever data they were able to access to, because not all data centers are created equal, right? A data center that is cooling their systems with electricity versus water will have a smaller footprint, potentially. If they're using renewable energy versus fossil fuel based energy, they will have a completely different footprint, right? So this is the part where having more information will help us have more accurate understanding of what we're dealing with, because we don't have it now, right? But this is the data that is available and what it shows. Okay, trying to get rid of this picture thing on my side that keeps floating around. Okay, so what as I was mentioning, one of the big issues with this space and the fact that it's growing so fast is the lack of transparency. And it's not that there's a lack of transparency because people are running away from their obligations. It's just that we're still in the chaotic phase of this growth, and there's really no standards or requirements for anybody to do anything in this area, right? All the disclosures that are made are voluntary primarily, and I'll talk about that a little bit later. They're voluntary, and they tend to be done in aggregated form. So for instance, when Google or Amazon or Microsoft say we consume this amount of water per year in our operations, it doesn't really break it down into what went into cooling the data center versus what went into something else, right? And the different scopes that I talk about, they are basically just providing a number. And so that's part of what we need, as society, is to organize ourselves to require and provide guidance and standardization to that. Okay, but let me just say a few thoughts about this on the transparency. Is that even in the case of when we have AI model cards, which are these cards that are supposed to provide information about how much, what is basically the footprint of training a AI model, most of the information tends to be on the energy side and the carbon side, because that's been a big emphasis of the last decade, right? In the environmental ESG disclaimers and all of that. So people were very focused on the carbon footprint and the energy, which is, I'm not saying it's not important, it's absolutely important. But I think it's time for us to start paying attention to the water as well, because it's really important given that we don't have so many available in the planet. Um, so I just believe very strongly that this is one of the things we need to prioritize is the greater transparency, not only because it will allow for better management of the resources. You cannot really manage what you cannot measure, right? It's impossible. But also, right now, it's hard for the broader community and the scientific community to innovate if we don't have the data that helps us understand where we're trying to go. And then this is something that I believe strongly that, I wanted to share is that I feel like right now, me individually and all of us, we are very uninformed consumers of our technology, right? We have our phones again, we have our picture, our data. We have no idea where this is stored. We don't know what the footprint of that environmentally is. I don't know how much water I'm consuming with all the pictures I have in my phone and in my computer. And I don't have a saying. I don't have a saying at all about where to choose to put my things, right? And I feel like hopefully there will be a time where we can make that choice. And my kids always laughed about this because I'm really into nutrition and she's like, you have to bring nutrition into this. But I always think about, I don't know if you remember, before 2010, there was no mandate for you to know what was included in your drinks if you went to a fast food place, right? And then after that, you go to Starbucks, and now it says if you get a Frappuccino, it actually tells you exactly what you are consuming. Before you didn't know that you were consuming about the entire calories you should get in a day in one drink. And I'm not trying to put down Starbucks because I love to go there, but it's just true. I just feel like transparency really empowers consumers to make an informed decision. It doesn't mean I'm not going to drink it now, but I know what I'm doing. And I feel like in terms of technology and our digital footprint, we are not there yet or even close to it. Okay. I was just going to stop for a second to say something. I have a lot of slides, uh, Sam. So if I start going too long, could you give me a warning 15 minutes before in case I lose track so I make sure that I'm allowing time for questions. Okay, thank you. So what I was going to say is that I've been saying there's all these problems. We use a lot of water. I wanted to make sure that I say that there's been a lot of innovation happening and progression in that area. So it's not like people are sitting on the sidelines trying to do nothing. And they've been trying to do a lot. And because one of the motivations is that generally what's good for the environment is good for the bottom line. So when you want all these models to be more efficient, it means you can run them faster and you can consume less energy. That means you actually potentially making more money out of it. So there's a lot of incentives out there for people to do the right thing from an environmental perspective. And there's been a lot of improvement even in the efficiency of data centers and their reliability and how much energy they're consuming and the cooling efficiency. So there's a lot being done. But given the place where we are now in terms of the technology, there's still an expectation that the AI global annual water consumption, so the amount of water that's going to be consumed by AI or the data centers that are where it's being run in 2027 will be between 4.2 and 6.6 billion cubic meters of water. And that, just to give you an idea, is about 4 to 6 times the entire water consumption of a country the size of Denmark. So it's significant. So one of the things that we've been exploring and we're really interested in is on the trade-off between water and energy. Because when you're cooling a data center, you're basically making this decision constantly. Whatever system you choose, you're either going to use more energy or you're going to use more water. And so our question was, why don't we all transition into energy-based cooling systems so we stay away from the water? And And I put this picture there on the left, which is from, so we didn't create that, it was some other colleagues. But what it shows, just very briefly, so you don't have to pay too much attention, at the bottom in blue is the amount of water consumed by, so these are four different types of cooling systems, right? And so in blue is the amount of water. The light blue is the direct water, so the scope one that you consume for cooling the system. The dark blue is the water that went into the energy generation, so that's scope two. And then the other dots on top, the orange, are energy consumed. So what you see is that in the cases where we're using energy-based systems instead of water systems, like the third one you see in that picture, you have much less water consumption, make sure it makes sense. You have, of course, more energy consumption, which makes sense. But then one thing that I wanted to point out is that even when you're running the system on energy only, because of the water footprint of that energy generation, you are not getting away from not using any water, right? So it's better, but it's not completely gone. So the question would be, can we just use renewable energy? And that would allow us to not use any water or very little, right? And so what I put on the right there are two maps of climatologies. The first one, it was created for USGS, and I actually should have had that there. And it basically shows us the water limitation in the United States. And you're probably all familiar with this. There's areas of the country, as I said, it's not evenly distributed. There's areas that have much less water and struggle with water. And then we actually see from the bottom one, which is the National Renewable Energy Lab climatology for renewable energy for the country, that there's plenty of renewable energy that we could use in the areas where we don't have much water, especially if we're thinking about solar and wind, which are great sources of renewable energy. But the downside is that, as I said before, data centers need very reliable and continuous power supply. It cannot be interrupted. We cannot accept the seasonality of and the diurnal cycle of solar and wind energy, which are intermittent, right? You have, at night you don't get it, or you might get wind but not solar. Like there's a pattern to when that energy is available. And that would be okay if we had good storage solutions that could store that energy and that allow us to use it later, but we're not there yet. So there's a place where innovation needs to happen and could potentially help us go to this new place. Okay, I'm just going to go very quickly and jump into why should we care in Illinois. So I'm back to that map where we have that 222, which shows us that Illinois and the Chicago area is one of the largest hubs for data centers in the world. And doing a little bit of research, I found that one would expect, the majority of those data centers are in the Chicago metropolitan area. There's a considerable amount in Aurora as well. And then there's a few sprinkles through the other locations that I listed there. And the main reason why they selected this location was, as I mentioned before, this is a very strategic location, abundant land, robust fiber optic systems and infrastructure, and the proximity to those economic networks. And so that makes it a very appealing place to put data centers. What this means is that we have a certain amount of water available in the state. There's all these competing sources of competing interests in using the water that we need to satisfy, and we've been doing that, right? And now it just means that now we have to add one additional pressure into the system. It doesn't mean it cannot be done, but what is important is I feel like we've been experiencing that throughout our entire lives, is this siloed approach of looking at problem where you solve one problem in one place and then you kind of like push it to some other part of the system. And I feel like we cannot manage those issues anymore that way. So when I'm talking about let's look at this with the framework of system of systems, is recognizing each one of those elements and many others, they're not here fully represented, are a system in itself with its complexity. And if you're going to solve these big, complex, wicked problems, we need to look at them as a system of systems. So you add an additional system to it, and you need to look at it holistically, or you're going to solve one part of the problem and create problems somewhere else. Um, so the real question here is, how do we support the growth of this technology, which is very promising in many ways, right? And I'll mention some examples. But how do we do that in a way that minimizes the impact of all this, in the communities and the people that where they're going to be implemented? And so that holistic risk assessment, I think, is super important. Uh, Increase that transparency. A lot of opportunity to adopt circularity principles. So this idea of using closed loops. If we don't have enough water, can we find a way to maybe use water that is not necessarily fresh in a system and recycle it or extract things from it that are not needed but are necessary somewhere else? Can we start thinking more about those approaches? We need a lot of research and innovation for sure to support this space. And then we need some guardrails, right? We need some guardrails to ensure that while we don't quite know what we're doing, we're not going too far, that we're going to create unintended consequences that are hard to deal with later. And I'll talk about the climate change in a second because I'm going to jump into that conversation. But one of the things that is interesting is that even if there's not much transparency right now, there's a push from the financial markets for that transparency to happen and for that understanding of how to manage resources to be more efficient. Because, for instance, Moody's, who rates, you're probably all familiar with it, does the ratings for in terms of risk for a lot of the big companies, including the data centers, has stated that now data center water consumption has emerged as a credit risk for those businesses. So there's other forces, market forces at play here that can really help make this like a real topic that we need to start looking into. Okay, so I'm just going very briefly through something because one of the things I wanted to talk about is, okay, we have a certain amount of water. We are used to the system receiving water in a certain way. And now, as I mentioned, things are changing, right? They are. It doesn't matter the attribution. Why is it happening? Humans are doing it or not. We're seeing changes in the system, in the weather and in the climate. And things are becoming pretty expensive to deal with in terms of life, but in terms of material consequences. And I put this image here because it really illustrates how the Midwest and the area where we are is pretty exposed to a lot of this impact. So this is the $1 billion disaster program, which unfortunately NOAA ran until recently, and it was just discontinued. But they put out the data for 2024, and they had identified and confirmed 27 weather and climate disaster events that exceeded $1 billion in expense. In addition to that, the National Climate Assessment had identified that a large number or several Midwest states are among the highest in the nation with the total number of loss for weather and climate impacts. So this is a vulnerable part of the country. And so that means that as the weather and the climate change, the hydroclimate will change it as well. And so the water we have available now and how we get it is going to change and is changing already. Uh, and the consequences is that the water is like a baseline for a lot of other things, right? And you all familiar with that, but I just put some examples here. There's a lot of systemic interdependencies between the water system and other systems. So when the water system collapses, other systems will be impacted as well, like urban systems, transportation, energy, health, and agriculture is a big one for the Midwest. Um, and we are already seeing some of those changes. So the Midwest, you probably all know, is responsible for, it's responsible for about 30% of the world's corn production and 32% of soybeans. Those are the latest numbers I've found. And what we're seeing is that the excessive spring rainfall is already impacting the production. In some cases, we see reductions of about 37% in the corn production, even if overall, the season is growing well and things are doing well, but just the fact that we have to push 1 month back the planting of the crops because of the rain is creating issues. And unfortunately, the projections, so those climate projections, when they are looking into the future, are showing that for the Midwest, we have an increase in extreme weather events. We have a reduction in the summer precipitation, which means that we'll have likely more droughts and will impact the irrigation and the need for more water during that period. And that will have uh, more heavier spring rainfall and more extreme rainfall events in general. And I'm not trying to be negative or get anybody depressed here. It's just like these are things we can deal with, but we need to understand and anticipate, right? And the key issue is that our systems have been designed for a certain hydroclimate, right? And for certain conditions. And sometimes they get pushed to extremes that we cannot deal with. And so that you know, I don't think I mentioned this, but I work remotely from Asheville. I go up there often, but I am seated in Asheville, and you probably all uh, recall it wasn't long ago that we got impacted by Hurricane Helene, and it was devastating. It was devastating even for parts of the city that had been accounting for all these changes in the weather extremes and had made some adjustments. Like, for instance, in 2024, no, 2004, the city had created a bypass in our water system because it had been impacted by Hurricane Ivan, and I forgot the name of the other one. Anyway, so they decided, well, we need to create more resilience in our system. So we're going to bury the main distribution line from the reservoir that serves about 80% of the population in Asheville. We're going to bury 25 feet underground. And there's no way anything is going to hit that. We're going to be okay. Well, sure enough, Helene had so much force in that water. It dug down 25 feet, pulled that pipe out. I don't know if you can see the size of the people on the side on top. But that's, this is the massive amount of soil that was removed with the water from the hurricane. And basically, it really destroyed the water system completely. We were almost 2 months without any potable water, and it was tragic. But anyway, it just means that we need to start rethinking about our systems and planning for these changes that are going to be different than what we had before. So I don't want to end without bringing the highlights the good part of AI, because I want to make sure that we keep that in mind. Uh, I am definitely not, again, as I said, I'm not trying to say we should completely stop all of this, because the potential is enormous and we're seeing it. We are seeing it in many different areas, and I just put a few examples here. And I also put some examples of how the big companies that are putting those data centers out there are actively working actually with communities to use AI to solve some problems in those communities, including in the water space. But the potential is really significant, and we're seeing those changes. We just, again, want to create some better understanding of what it means to put these data centers in our backyards and how to better manage that. So I just want to jump for a couple of minutes into the center that I'm running, because it's there in your backyard, and I want you to know a little bit more about it in case it can be helpful to support you in any way. Well, we're basically looking at this problem, many others in the water space, and leveraging a lot of the principles of engineering, science, and technology that we have in our department and in the collaborations we have around the world to manage some of these wicked problems, right? And we're trying to position ourselves as a think tank. Primarily, we do a lot too. We don't just think, but we really want to look at this complex, forward-looking water-related challenges and try to understand what can be done about it. How can we bring our brains together? So the department has a lot of people, and the center has a lot of people that work on fundamental engineering and science problems, like basic knowledge that we need to know to advance the state of that space. But then there's a lot of work being done in the integration of that knowledge into solving real problems. So I'll just give you a very quick set of examples, but I wanted to just make you aware. These are some of the core areas we work in. We do a lot of work in risk and resilience of physical systems, including water systems, looking at the interdependency of different infrastructure systems. water and energy nexus, emerging contaminants like PFAS. We're exploring more of that water of that space. Water extremes, the circular water economy that I mentioned before. Can we use these closed loops to leverage existing water instead of taking new fresh water? Freshwater security, waste management, a lot of those things. So, and the idea again is that we need to have all these concepts come together and look at it holistically, because the ultimate goal is, can we create this robust and resilient water systems that if we hit them with some extreme event or a man-made disaster, can they stay strong enough and maintain functionality, or are they resilient enough that they're going to come back to the state where they were, or to a new state where that functionality would be restored? So that's the ultimate goal of what we're trying to look at. We Again, as I mentioned, we are in the civil environmental engineering department. We have an extensive and very knowledgeable faculty, and then we also have a connection with the National Center for Supercomputing Applications, which help us have access to like more advanced computational resources. And I just put the ranking there, not to brag, maybe just a little bit, but the main thinking there is that because of the ratings and how well positioned we are in the country for civil engineering, it gives us the opportunity to really attract really good students, undergraduate but graduate students, and so that's a plus that we can leverage in the center as well. And we have, I don't know how many of you know, but we have an extensive number of like state-of-the-art facilities and laboratories that are like at the national and international level recognized. And let me see my time to make sure we have enough time. I'm just going to go through this really quickly. I just had a couple of examples, more than a couple, a few examples of work that different colleagues are doing in the center. And I was just going, but I'll go through them really quickly. But just to give you an idea, for instance, Anna Barros, who is the director of the center, actually a lot of our work is focused on hazard prediction and, like, for instance, try to better estimate flash flooding and conditions like that by using a lot of AI, neural networks and satellite data and things like that. So again, a use of AI in some of these solutions. Another colleague, Ximen Kai, does a lot of the work, is really an expert in systems of systems and water systems. And he does a lot of work in the circular economy that I mentioned before. Marcelo is an expert in hydraulics and sedimentation, and he actually does a lot of the work with the city of Chicago in trying to understand and model the water systems in Chicago. Paulo does a lot of work, and the risk is really a infrastructure structural person, and he does a lot of extensive work in the risk analysis part of the equation, not just for water systems, but in general for infrastructure. Alex does a lot of work, for instance, on groundwater modeling and monitoring, and using the digital twins and AI and machine learning. So that's another application that might be useful. And I'm closing now, and I'm going to just give you a few takeaway messages, hopefully. One is that AI seems to be here to stay. And so we can close our eyes, or we can bury our head in the sand, or we can do whatever, but I think it's here. And so the question is, what can we do, again, to embrace that change, leverage it, maximize the benefits, but minimize the costs that it brings? It can help us solve a lot of problems, and we are seeing that already. So it's not hypothetical. We are seeing those changes happening, and some of them I consider really transformational in the way we're solving problems. But we don't fully quite understand its environmental footprint, right? Because it's so new and it's so undefined, the space, and it's growing so fast that we are trying to keep up with it, right? So I believe that more transparency is really important, and setting some guidelines and some standardization for that is really important. And I wanted to mention also that one of the things that I believe could help communities like the ones in Illinois and everyone else is to have better coordination. There was a recent report that came out from the National Academy of Science on data centers, it was primarily focused on the energy part, but a lot of the conversation was about how these decisions about incentivizing data centers to come to different communities are made by politicians that are not necessarily understanding the implications for the regional and the state level in terms of resource consumption, right? So, and this is again, there's no data. It's really hard for them to do that. But how can we help policy people understand the bigger picture of what needs to be done to better manage these resources? So, and the other thing is that can we ask these data center providers and these corporations to give us a little bit better understanding what they are bringing to these locations, because not all data centers are created equal. Some, again, as I mentioned before, the cooling system they are using, is it water, energy based? Is it hybrid? Is it some immersive systems? There's many options out there, has different implications. What kind of energy are they planning to use? How often are they going to use? What's the size? What's the impact and the footprint? And I think requesting that information seems completely logical to me, and we are not really necessarily doing it the level that we need. So, anyway, I think that's all I had to say. I'm going to thank you for your time and your patience, and hopefully this was helpful in any way. So, thank you.
All right. Thank you so much. Does anybody have any questions? All right.
Okay, we've got a question. Hang on just one second. I was just curious if there were any groups that lobby politicians for these very guidelines that you're looking for.
So there's something starting to emerge. So the CDP, which was the old climate, oh, I can remember now, disclosure project, now it just goes by CDP, has some general guidelines in general for any industry. And some of them are providing guidelines for how to disclose water. Again, it's all voluntary. So right now, there's nothing that is mandatory. There's some industry specific, like green industry. Some of those associations and professional groups are trying to push for more specific disclosure guidelines. And what we're seeing is that Europe is a little bit ahead of it. They've been traditionally ahead in terms of requiring more disclosure of risk and footprint and environmental impacts. So I think we'll likely start to see more things coming from maybe Europe and other countries. And for all these big companies like AWS and Google and IBM, all of them are international, right? So they will have to start modeling some of those requirements externally, and it will be easier to bring it here at some point when we push for that internally. Does that answer your question?
Yes.
Yes. That's
Thank you.
question.
One of my daughters shies away from using AI because of the resource usage. And she's heard the same sorts of things that a conversation with ChatGPT, creates so much of a pull on resources. And I've always wondered, like, if 5 more people use ChatGPT today than used it yesterday, does it really use incremental resources, or are those statistics just taken by, how much energy or water is used during a day, and dividing it by the average number of interactions?
Yeah, that's a great question. And it just goes back to that lack of transparency. I don't know if we know that, because the data is not being made available for us to understand if this is like, is this a linear process, or are there efficiencies that kick in once you have a much larger number of people using it? So yeah, that's a great question. And again, it goes back to allowing us as consumers to understand our role in this process, which we don't fully know, because I really think this is not just responsibility of the tech companies. Of course, they hold a big part in this because they are controlling most of the process right now. But as consumers of this technology, we have a role to play as well. But we need to be given the information so we can be more responsible in our use of the technology as well. So, thank you. I'm afraid I don't have a clear answer for you.
Okay, anybody else have any questions? All right, I think that might be it. Well, thank you so much
Okay.
again for all your time, Dr. Prevet. We really appreciate it. It was lovely to have you.
Thank you very much. And if anybody wants to follow up, feel free to put me in contact. I'm very happy to follow up and help in any way in this space. So thank you
Right.
all for your time.
Thank you
Bye
so much.
bye.